Hi, I'm Ben Peterson, and this is my friend Brett Brooks, and we're both pre-service teachers here studying at Virginia Tech, getting our masters, and we're going to be talking about exponents today.
So we're going to progress through what it means for an exponent to be a natural number. We'll add in 0 along the way as an exponent, go to our integers all the way through rationals, reals, and we're going to conclude with a discussion of what complex exponents could possibly mean. So we'll begin with the natural numbers.
You probably want a definition first.
Definition of an exponent.
What an exponent is.
So an exponent, we're going to define in this sort of term where we'll say A is a base, and the exponent is this power we're going to raise our base to. We'll kind of define what that means progressing through the different possibilities for the exponent. And so we're going to begin where x is in the natural numbers. So that's things like 1, 2, etc., etc. So this is the intuitive start for exponents. So say we want to do a squared. Well, that simply means we're multiplying a by itself one time. So we have two a's. We're taking the product a to the fourth, a times 4. Geometrically speaking, we'll say, hey, if we've got a unit, and we'll say this is 1 unit, if we want to square it, like you might expect, a unit squared is going to create a square, where the area is 1 unit squared. If we want to cube the unit, we'll imagine this coming out of the board here. We have a nice cubed unit where the volume throughout is 1 unit cubed.
Okay, so generalizing that to, let's say, a non-standard is 1 unit. If I have a length now that's 2 units long, it's a terrible straight line. If I have a length that's 2 units long, we have now here's a 2. If I were to make that into a unit squared, I will turn this into a square by making this length also the same unit, or 2 units. And now the area on the inside of my model will be composed of 4 parts of this 1 unit, because we have 2 times 2 is 4. Here we have 2 sets of 2 or 2 sets of 2, either way you look at it. You have it as 2 rows or the 2 columns of 2. And that gives us 1, 2, 3, and 4.
4 square units. So from our discussion of our natural numbers, we can develop many properties of exponents that we're going to want to carry throughout as we expand what our exponent can possibly be. So
expanding the domain for which our exponentials lie on.
The domain that's defined on, yeah.
To use some fun terminology.
So if we have our a, we'll say raised to some exponent m in the natural numbers, and let's say m is equal to n plus p. So a raised to the m is going to be a m equals a to the n plus p. Well, by the way, we define it over here. That's just going to be the same thing as, whereas a to the m is a multiplied by a, where that is done m times. Since m equals n plus p, down here we can say this is a again, but that is also, we'll say these are the n times here, and then the p over here. And so we can split this up because multiplication is associative. We can split this up into a few different products, 2 to be exact, where we've n times here, p times here. And by the way we defined our exponents over here, we're going to be able to say that this is a to the n times a to the p. So when our exponent is a sum in our natural numbers, we can split it in this fashion. Similarly, we can see properties where,
so if we have a sum for a base and something in our exponent, it turns into a product of the bases raised to these exponential powers. So to put that into a concrete kind of example, if we have something like 2 to the 5th, that is 2 to the 2 plus 3. Also can be expressed as 2 multiplied 5 times, or 2 multiplied 2 times, multiplied 3 times. Not 3 times, that's bad. So like if you break it off here, you can see you have 2 and 3 and 5. So if you want to have a sum in your exponent, you can break it up into 2 different parts just looking at what it means and actually combine it together. So you can put this as 2 squared and 2 to the 3rd for this part.
so that this equals 2 squared times 2 cubed. So similarly, we'll add another property down here.
I'm just going to put this over here so we have a list of our own properties.
Similarly, we can assume our exponent is a product instead of a sum. So if we have a2, we'll say the b, where b equals, we'll say c times d. That's a to the c times d. We have a product. So what does that mean for us? Well, this we have understood to be a multiplied by itself, b times, which we're defining b to equal c times d. So that's going to be the same as if we multiply a times itself, c times d times. And so what we can do is we can split this up to say, well, why don't we multiply a, we'll multiply it by itself c times, and then we'll multiply that whole thing by itself, whatever this is, d times. So we're going to have some value here. We've done it c times. And then we're going to rewrite that.
So you're rewriting the set of parentheses of a to the c d times. You're multiplying the whole a to the, he's multiplying the whole a to the c expression right here by itself d times. So it's a to the c to the d.
And because we know, again, by associativity and multiplication, we can see, we can look at it like this, or we can just get rid of all our parentheses, and that's just multiplying a by itself, c times d times, which is the same that we did here. So we can see that a to the c times d, we can look at it as a to the c raised to the d power.
So you want to use some actual concrete numbers for this?
Yeah. So let's say we have, we'll go in here, 2 to the 6. So we're raising 2 to the 6th power. That can be rewritten, because we know 6 equals 3 times 2. We can rewrite that as 2 raised to the 3 times 2, which we know equals 2 times 2 times 2 times 2 times 2 times 2. But we can rewrite this, of course, as 2 times 2 times 2 times 2 times 2 times 2, which is just to say 2 multiplied by itself 3 times, twice. So this is another example here. So we have these two properties. We have We have a sum, and we can split into a product. We have a product which we can pull one of them outside of parentheses here. Similarly, we can see that by this same kind of logic that our subtraction, so if we have something like this, a m minus n, we'll consider what that means once we're So we have a, and we're going to multiply it by itself, as we've said, m minus n times. So let's start with a concrete example to think about this. We'll do 2 raised to the, let's say 4 minus 2. On the one hand, we know this can equal 2 raised to the 2, which we know what that means already. That's just 2 times 2. Okay? So here, how can we split this up? We know we need to get 2 times 2. How can we split this up to make sense of that? Well, this is just to say, hey, we're going to multiply 2 by itself 4 times. And then we know we need to get back down to its just twice. And so we need to divide by 2 times itself twice.
And the way of thinking that is, we multiplied by 4 times, but now we want to multiply by 2 less times. So we're going to do the inverse of multiplication 2 times. The inverse of multiplication is division, so we divide 2 times.
So we know that these are going to cancel out and leave us with our multiplicative identity of 1. So we have 2 times 2, which is what we knew we needed to get over here. So our general property we can put as follows. When m is greater than n, we're going to be left with this, correct? Mm-hmm. And if n is greater than m, then by the positive and negatives, they're going to end up switching, and we're going to end up with.
However, we only have natural numbers right now, so this only works right now when n is bigger than n, because you don't have non-natural number exponents yet.
So we'll add this property.
Provided that n is greater than n.
Right. We'll add this to our list over here.
Is there anything else we do right now?
When n is greater.
Alright, so we're going to examine some special cases before we move on to the integers. So we know that we've defined exponents to be repeated multiplication of itself. So there are 2 very special bases that kind of are not outside the rules, but play tricks with these rules. So the first base we're going to look at is the base of 1. If I raise 1 to any exponent, doesn't matter what, 1 to the x, it's going to mean 1 multiplied by itself x times. But we all know that 1 times anything is just itself, so 1 multiplied by itself any number of times is going to be 1. So it doesn't matter what exponent you raise 1 to, it's just going to stay as 1. So 1 to the x just equals 1. Doesn't matter what rule you have to use with it, if it's just 1 raised to any exponent, it's still just going to be 1. Similarly, another value that doesn't really play by the rules in multiplication is 0. 0 doesn't have any product, like there's no product that involves 0 that's not, it's going to be non-zero. So anytime you have a 0 base, again, doesn't matter what the exponent is, we can say it's y now, 0 to the y is also going to be just 0, because anytime any amount of zeros multiplied by each other, still just going to be 0.
All right, so now we want to move to integers from our natural numbers. So we're going to need to add 0 as an exponent, and we're going to need to add negative natural numbers. So when we do this, let's revisit again this property we established earlier. A to the m minus n equals a to the m divided by a to the n. And say we have an example like this. earlier we specified, hey, m is going to be greater than n, but what if it's not? So what if we had 2 raised to the 3 minus 5? If we're going to extend our definition to expand beyond this, we would do 2 times itself 3 times, and we divide by 2 by itself 5 times, okay? We know what this equals. This is going to be 2 to the negative 2. 3 minus 5 is negative 2. And what's that going to need to mean then? So these are going to cancel, right? That's going to be left with 1, it's going to be left with 1, that's going to be left with 1. And so we're going to have 1 over 2 times 2, or 1 over 2 squared. So we started with 2 to the negative 2 as it turned out, as we move this way. And we showed, hey, using this property, when we extend it to when, no matter what, hey, m and n are, we extended it and showed, hey, 2 to the negative 2 is going to equal 1 over 2 squared. So we're going to add that as a property. We're going to say, okay, a to the negative n is equal to 1 over a to the n. Generally, we'll start with something like this. You can see it this way. 1 over a to the n, 1 over a n times. But what if n is some difference where we say, all right, so let's assume we have, to show this guy, let's assume we have r minus s equal to n, where r is greater than s, and n is going to be the difference between the two. And then we'll say, okay, well, what about s minus r? Okay, that's going to be just negative n. We can see that by distributing it. We multiply this by a negative 1, we can multiply this by a negative 1, and it's just going to swap them. So what will we have if we raised a to the negative n? Well, we have a to the s minus r. When we have a raised to the s minus r, we know from over here, let's write it this way. A, that's going to be s times over r times. But we know r is greater than s, which means we're going to have more a's down here, as I kind of indicated, than a's up top. We're going to be able to cancel them all out. But we're going to be left with the difference. We're going to be left with n a's on the bottom of our quotient, which is going to be 1 over a, well, that's n times. So we can generalize just like that, where we started with a raised to the negative n power. So we saw a specific example, then we saw in general why this works. Now, all that's left for us to consider in the integers is what could a 0 exponent possibly mean. So we have some expression, a to the 0 power. Well, it no longer makes sense to multiply a by itself 0 times. What could that even mean? It didn't for the negative integers either, but we kind of worked with that. And so what can we do for this? Well, we know that 0 is equal to, since it's the additive identity, any number minus itself. We don't want to use a, that'd be a little confusing. So let's do b. Okay? So we can rewrite this, a raised to the b minus b. But we know over here, and we can even erase our condition here. We still need to check when m and n are equal, which is what we're doing right now. So a to the 0 equals a to the b minus b from over here. Okay, we can write this as a raised to the b divided by a raised to the b. Well, that's 1, pretty simply. So we know a raised to the 0 is going to need to equal 1. So we'll write that again over here. And so that's going to complete the integers. All right?
There is one quick exception to make to that. We talked about earlier special cases. It works when a is 1, but when a is 0, we are left with 0 over 0, which is the indeterminate form, and we cannot use this argument to say that 0 equals 0 equals 1, 0 over 0 equals 1. This is not true. 0 over 0 is indeterminate. There's countless arguments for why it can't be 1. Don't use that argument. Just don't.
So we'll add down here
A is not 0.
when a is not equal to 0. So now we need to move to our rational numbers. So we're going to add things like m over n,
Where m and n are.
where m and n are going to be integers. So what could an expression of this form mean? Let's look at it. Let's first consider when m equals 1. So we'll let m equal 1, and we'll look at a raised to the 1 over n power. Okay? To consider what this means, let's think of an example. So we'll say 2, and we'll go to the 1/3 power. Okay? What would happen if we multiply this by itself 3 times? That's what we defined it to mean, right? So we have this property, correct? So we can use it, since we're going to extend these properties as best we can across. We're going to extend this to 2 raised to the 1/3 times 3. But 1/3 and 3 are what? Multiplicative inverses. That's just going to be 2 to the 1, which is going to equal 2. So going back then, we started here. So what this is saying is we have some value, whatever that could mean, cubed is equal to 2. That's the same thing as what we define the cube root of 2 to mean, right? The cube root of 2 multiplied by the cube root of 2 multiplied by the cube root of 2 is 2, by definition of cube roots, okay? So we see that 2 raised to the 1/3 power, what does that equal? Well, it equals the cube root of 2, okay? We can generalize that pretty simply. To say that a to the 1 over n is going to equal the nth root of a. Okay? Let's see, where can we add this property? We'll put it right here. And this next step was almost implied in the example we just showed. A raised to the m over n, and we'll say m is no longer 1. A raised to the m over n, okay, what does that equal? A to the 1 over n to the m. And so we just did that. So what does that mean for us? Well, a to the m over n is going to equal, well, nth root of a raised to the m power. where m is an integer, and we already explored what that means.
Does it matter which order we do the root and the power in?
We could also do it the other way, the other order. So let's consider why that's the case.
Well, it should just be the case because multiplication is commutative, so using this rule right here, we can say it's the same thing as a to the n times n instead of n times n. So it really doesn't matter which order you put it in. You can put the exponent inside the root or on the outside, both same thing.
So this is going to equal
The nth root of a to the n.
n of a raised to the n.
Same thing.
And that makes sense because we can think of an example where, let's see.
I mean, you can just switch these right here.
Yeah,
That's all you need to do.
to make it general.
Alright, so we've just explained how we can deal with all rational exponents. Now the tricky part is to deal with an irrational exponent. We just defined basically how to multiply 2 by itself like a half of a time. So the real question is, how do I raise 2 to something like the pith power? What does that mean?
I have no idea.
How do I multiply something by itself an irrational number of times? The answer is obviously you can't. We don't even know what the exact value of pi is, so trying to find an exact value for this thing itself is an impossible squared to use to use exponents. So what we do, and what calculators actually do, is we do limits. We take a look at how sequences approach these things, what happens when we get closer to these irrational numbers. So if we wanted to look at, as we're getting close to pi, we can pick values closer, like 22 over 7, or it was like 49, no. You do things like 22 over 7, or you do things like, or even closer, 153 over 49, and you just keep getting closer and closer and closer like that. And you take the limit of these values using our rational expression here. You take the limit as they get closer and closer and closer to that irrational value that you're trying to approximate. You don't actually ever find values for these expressions because, to be frank, they don't actually exist in a cutoff form. You can get to a certain degree of precision, but after that, it's not certain. So generalizing from the rationals to the reals, all you actually have to do is take a limit of sequences that get closer. So that plays a huge part in our complex definition of exponents. For a complex exponent, we have stuff in the form a, no, I don't want to use a. So you c to the a plus bi, where b is the coefficient of your imaginary part, and a is your real exponent power part. Okay, so the way we usually deal with this is we like to split it up using our rule right here. We like to split it up as c to the a times c to the bi. So whenever you're looking at this, this is a real coefficient to your c bi, or c to the bi term. Now, when we're dealing with the complex plane, we have a geometric representation. We have our complex axis like this, or our imaginary axis like this. We have our real axis going this way. Real, this is complex. So these are like our a's, and these are our b's. Why do we do? Oh, the reason we do this is because we deal with rotations. We take this real axis and we're going to rotate it up to this complex axis. And the reason that works is if you take our real line, just imagine a bunch of values going off towards infinity. And if we wanted to, here's our 0 point, if we wanted to take all of our real values here, so like a, and flip it over to here negative a, we multiply by -1. we multiply by -1, what we're doing is we're taking this axis and rotating it all the way over here, 180 degrees. And that's through a -1 multiplication, or multiplication by -1. So multiplying by -1 does a full 180. What takes us halfway? Well, you wouldn't multiply by a full -1, you'd multiply by a square root. So the square root of -1 is that very famous number. We gave it its own letter. It's the imaginary I. So if we're looking at our complex plane, it should make sense that these two are right angles of each other because these are all of our real values multiplied by I. So our complex plane is formed by this perpendicular intersection of our reals plane and our complex plane. So what we're going to do now is we're going to generalize this to a form e to the a plus bi. Actually, I don't want to use a and I or b anymore. Let's go with a to the x plus yi. The reason I'm doing that is because this e gives it a very special derivative property, but we'll get to that in a second. So to generalize c a to the bi to e to the x plus yi, what you have to do is you have to find out what exponent takes c over to e. So if you were to solve this equation right here, we'll call it d. C to the d equals e. You can solve this equation for any value c. You can find a d such this works, so long as c is not 1 or 0, using those two exceptions. So after we find this d value, we can divide, or we can factor out a d from here, and then you can do a substitution that makes it into this form. So from now on, we're going to deal with exclusively this e to the x plus yi. Alright, so we're going to have to look at what this means in this plane, right here. We're going to break it up into those two parts again. We're going to have e to the x times e to the yi. And we're going to look at specifically what the derivative of this is. The reason we're going to look at that is so we can see how it's behaving on this plane. It's not going to behave like we normally know the e to the x function. The e to the x function looks like this, but that's when you're mapping real values to real values. So that, honestly, on this graph, would just kind of look like us rotating back, or oscillating back and forth on this. That's not going to be very interesting. We have to figure out how this behaves in our complex plane. So looking at the derivative of this, if we take the derivative with respect to x, this is a constant. Derivative of e to the x is just e to the x. That's not that interesting. Again, it's just going to be moving back and forth on the real plane. What is interesting, though, is if we look at the derivative of this with respect to y, the partial of this whole thing with respect to y, we get, this is just a constant, right? X is not part of y, so x is just going to be a constant. So e to the x is just going to stay there as a coefficient. And then we're going to take the derivative of this e to the yi stuff. This is going to have to use the chain rule because we have a non-variable coefficient. It's got more of a composite function kind of thing to it. So the derivative of e to the x, or e to the anything, is e to the anything. So it's e to the iy. But then we get times this very special I. This means we take wherever our current vector is in the plane. This is where we started with. This is our position. We take that and we multiply it by I. We take that times I, that multiplication by, or that rotation by 90 degrees, and that means we take our vector, we'll say it's our arbitrary vector like this. That means we go 90 degrees. We go perpendicular to it at all times. This is our direction. This is our position. There is only one figure that has a direction that is continuously perpendicular to its position, and that is a perfect circle. Let's see if I can do this. That's awful. That is god-awful terrible. Anyways, close enough. So we have a perfect circle now. This part of our perfect circle tells us really how far out we go, how far our position vector goes. It tells us the magnitude along the real axis that we start on. We start somewhere on this real axis with this. It tells us, because we have no imaginary part yet, it tells us to go out a certain distance and then we'll stop. This e to the yi stuff is what gets us to be rotating along this. So that's where actually you can get Euler's nice identity from. If we wanted to figure out what any value e to the xi is, well, I guess I won't use x. If we wanted to figure out what this guy is right here, the e to the bi, all we have to do is go this many radians around our circle. If we had, oh, I don't know, pi, we can go pi radians around our circle. We'd start here. Our e to the 0 right here, actually. Well, this is assuming that a is 0. And we know e to the 0 is just 1. So our magnitude is just 1. It starts out here, right here at 1. And then it travels around the circle pi radians. So it travels around this nice circle until we end up here. So e to the pi I is actually just equal to -1. Actually just equals -1. We can do that for any value of b that we want. It may end up being very messy if you don't get like a multiple of pi. You might have to actually figure out using limits and sequences where you are going to end up in your unit circle. But for any a values and b values, you want to plug into this complex number. That's not an attribute now. For any complex values you want to plug in, this a determines how far out you go. You go out e to the a values along this. And then from there you go rotate that however many radians this b tells you to go. So you'll rotate up if it's positive, you'll rotate down if it's negative, and you'll go however far it tells you. So all you have to do for generalizing this exponential thing to the complex plane is scale out as far as your a goes, as that tells you to go, and then you take your rotation b radians. That should do it.
So we started with exponents that are natural numbers, and we saw that was fairly intuitively just multiplying the base by itself that many times. We used that to get properties like this one, this one, this one. Then we wanted to move to our integers, so we needed to add 0, we needed to add negative numbers, right? We looked at those properties, we saw this property, and we saw that a to the 0 equals 1. Whenever a is not equal to 0. We then moved to rational numbers. We saw that rational numbers are the form 1 over n, or the nth root, by examination. And then multiplying by m is fairly intuitively what we do for a to the m over n. Moving to the reals, we took limits of our rationals as they approached irrationals, and then we concluded with complex, looking at e as a base, and making a circle in the complex plane. So now hopefully you understand what an exponent means for any value in the complex plane that we could input as an exponent.